What are paradoxes, and why do they matter? A paradox is a statement or situation that seems contradictory but might reveal a deeper truth or expose flaws in our thinking. In science, paradoxes pop up when our theories, observations, or assumptions clash in ways that don't add up. They're like warning signs saying something's off. Instead of ignoring them, scientists use paradoxes to question established ideas, spark new theories, or refine existing ones. They're catalysts for breakthroughs, forcing us to rethink what we assume is true. Let's ground this with the liar paradox from our earlier talk. The statement, "this sentence is false," flips between true and false, revealing a glitch in classical logic. It doesn't directly impact physics or biology, but it's influenced formal systems like mathematics and computer science, pushing logicians to develop new frameworks. That's the kind of role paradoxes play. They expose limits and drive innovation. Key ways paradoxes shape modern science. Let's break down how paradoxes influence science across fields, with examples to show their power. 1. Exposing limits of current theories. Paradoxes often reveal where a theories break down. When experiments or ideas contradict what we expect, they force scientists to rethink foundational assumptions. Example, the ultraviolet catastrophe. In the late 1800s, classical physics predicted that a black body, an idealized object that absorbs all radiation, would emit infinite energy at short wavelengths, like ultraviolet. That's absurd. Objects don't glow infinitely. This paradox, called the ultraviolet catastrophe, showed classical physics couldn't handle energy at small scales. Max Planck resolved it by proposing that energy comes in discrete packets, or quanta, birthing quantum mechanics. Impact. This paradox didn't just fix a problem, it launched a revolution, reshaping our understanding of atoms, light, and energy. Quantum mechanics now underpins tech like lasers and semiconductors. 2. How it shapes science. When paradoxes show up, they're like a check engine light for science. They tell us our models are incomplete, pushing researchers to develop new theories or refine old ones. 2. Driving mathematical and logical foundations. Paradoxes in mathematics and logic, like the liar paradox, have reshaped formal systems critical to science. They challenge how we define truth, consistency, and proof. Example, Russell's paradox. In the early 1900s, Bertrand Russell asked whether the set of all sets that don't contain themselves contains itself. If it does, it shouldn't. If it doesn't, it should. This paradox exposed cracks in naive set theory, which assumed every property defines a valid set. It led to a overhaul of set theory, with systems like Zermelo-Fraenkel axioms, now the backbone of modern mathematics. Impact. Math is the language of science. Russell's paradox forced a more rigorous foundation, impacting fields from physics to computer science, where consistent systems are crucial for coding and algorithms. Connection to liar paradox. The liar paradox, like Russell's, deals with self-reference. It inspired work in formal logic, such as Alfred Tarski's separation of language levels, which clarified how we talk about truth. This influences computer science, where self-referential loops, like in the liar paradox, can crash programs or require special handling in AI systems. 3. Catalyzing new theories and discoveries. Paradoxes don't just break things, they spark new ideas. When observations clash with predictions, scientists often invent novel concepts to resolve the tension. Example, the EPR paradox. In 1935, Einstein, Podolsky, and Rosen proposed a thought experiment to challenge quantum mechanics. They argued that quantum entanglement, where particles instantly affect each other across vast distances, implied spooky action at a distance, contradicting relativity's speed of light limit. This paradox suggested quantum mechanics was incomplete, but experiments, like those by John Bell, confirmed entanglement as real, supporting quantum theory over Einstein's objections. Impact. The EPR paradox drove research into quantum entanglement, now key to quantum computing and cryptography. It turned a paradox into a cornerstone of modern tech. How it shapes science. Paradoxes like this push scientists to test theories experimentally, leading to discoveries that turn apparent contradictions into new principles. 4. Challenging intuition and expanding perspectives. Paradoxes often arise because our intuition, shaped by everyday experience, fails in extreme conditions. Resolving them expands how we view the universe. Example, the twin paradox. In special relativity, the twin paradox imagines one twin traveling near light speed while the other stays on Earth. When the traveling twin returns, they're younger because time slows at high speeds. This seems paradoxical. Why isn't time symmetrical for both? But relativity resolves it. the traveling twins' acceleration breaks the symmetry. Impact. This paradox helps cement relativity's acceptance, shaping modern physics, GPS systems, which account for time dilation, and our view of spacetime. How it shapes science. Paradoxes like this force scientists to abandon intuitive assumptions, embracing counterintuitive truths that redefine reality. 5. Inspiring interdisciplinary connections. Paradoxes often bridge fields, requiring insights from multiple disciplines to resolve. They encourage collaboration and cross-pollination of ideas. Example, the arrow of time paradox. Why does time seem to flow in one direction, from past to future, when fundamental physics laws are time-symmetric? This paradox, tied to entropy and the second law of thermodynamics, puzzles physicists and cosmologists. It's led to theories about the Big Bang's low-entropy state and connects to questions in philosophy and information theory. Impact. This paradox drives research into cosmology, statistical mechanics, and even consciousness, linking seemingly unrelated fields. Connection to liar paradox. Like the liar paradox, the arrow of time questions foundational assumptions, in this case, about time and causality. Both push us to rethink how we structure knowledge. Broader impacts on modern science. Paradoxes don't just solve specific problems, they shape the scientific process itself. Encouraging skepticism. Paradoxes remind scientists to question assumptions. The liar paradox, for instance, made logicians doubt whether all statements have a definite truth value, influencing rigorous scientific methods. Fostering creativity. Resolving paradoxes often requires bold, out-of-the-box thinking, like Planck's quantum leap or Einstein's relativity. Advancing technology. Paradox-driven discoveries, like quantum mechanics from the EPR paradox or entanglement from the EPR paradox, fuel tech innovations. Philosophical insight. Paradoxes blur the line between science and philosophy, forcing us to grapple with what's knowable, as the liar paradox does with truth. Why paradoxes persist? Some paradoxes remain unresolved, like the black hole information paradox, where quantum mechanics and general relativity clash over whether information is lost in black holes. These ongoing puzzles keep science dynamic, suggesting there's always more to learn. They're not failures, but signposts pointing to new frontiers. Wrapping it up, paradoxes like the liar paradox, Russell's paradox, or the EPR paradox aren't just quirks, they're engines of progress. They expose cracks in our understanding, force us to rethink assumptions, and inspire breakthroughs that reshape science. From quantum mechanics to relativity to computing, paradoxes have driven discoveries that define the modern world. They show us that when things don't add up, that's where the real discoveries begin.